Hello, everyone. My name is Anna Geib, and today we're going to be talking about capacitors and dielectrics. So let's start off with what is a capacitor? A capacitor is an element of an electrical circuit that's able to store potential energy through charge separation. So when a capacitor is hooked up to a battery, electrons will start to flow through the circuit from the negative anode to the positive anode of the battery. When the electrons reach the capacitor, they'll be unable to pass through it due to a plate separation, and the first plate capacitor will start to acquire a negative charge, and the second will start to acquire a positive charge. This will continue until the voltage difference between the two plates is equal to that of the battery. We can model capacitance between two plates by the equation C is equal to Q over delta V, where C is capacitance, Q is charge, and delta V is change in voltage. The separation of charges will also create an electric field between the two plates, which will then allow the capacitor to act as a battery if we say remove the battery and hook it up to a resistor. So now let's look at a few things that affect capacitance, or the amount of potential energy that can be stored. Capacitance is primarily determined by plate geometry. So the larger the surface area of the two plates, the more charge the capacitor is going to be able to hold. Additionally, the smaller the distance between the plates, the more charge the plates are able to hold, because the attractive forces from the oppositely charged plate will be stronger than the repulsive forces from the same charged ions on the same plate. Another thing that increases capacitance is the presence of a dielectric. A dielectric, or an insulator, is a non-conducting material that can be placed between the two plates of a capacitor. Dielectrics increase capacitance by inducing dipoles in the dielectric material, creating a second electric field between the plates. The second electric field will point in the opposite direction and will allow more charge to accumulate on the plates of the capacitor. So now let's look at an example of this. One cell in our bodies that makes great use of dielectrics is the neuron. The neuron is a fundamental unit of our nervous system and communicates with other cells and neurons through electrical signals. So here's a neuron, and the electrical signal is trying to communicate will need to travel down the length of the axon from the axon hillock to the axon terminal. We can model the axon of our neuron with this electrical circuit. We will call our first action potential promoted by our stimulus our battery. We will then have resistance from the axon plasm, or the jelly-like substance our ions are traveling through. And then we will have our membrane, which is the resistance an ion will face if it tries to travel back through the cell membrane. And in parallel with it, because an ion can only flow one way, we'll have our capacitor. And we're using a capacitor for this model because action potentials repropagate as they go down the neuron. So it will act our circuit as like flipping switches and allow our capacitor to then act as a battery for the next propagation. If we have an electric signal, our ions will move through the axoplasm a short distance where they will have the option to go through the membrane or stay inside the cell, separating charge and passing along the signal. Because an axon propagating a signal has a lot of positive charge inside the cell and a lot of negative charge outside the cell, the charges will be attracted to each other and want to diffuse towards each other. This will cause our axoplasm resistance to be really large and will cause our capacitor to take a long time to charge. And this is where dielectrics come in. So most axons in the body are going to be myelinated, and this means they're going to have a neuroglial cell, either a Schwann cell if you're in the peripheral nervous system, or an oligodendrocyte if you're in the central nervous system, that surrounds the axon of neuron, making it look kind of like a chain of link sausages. So we'll have our myelinated piece, and then we'll have our nodes of Ranvier between each. And in the node of Ranvier is where our signal will be repropagated and where we'll place our capacitor. So now if we look at our circuit with the dielectric, it's going to insulate the axon, which is going to reduce this interfering charge between the outside the cell and the inside the cell, allowing the capacitor to charge faster and allowing us to react and process signals faster. As you can see, dielectrics are really important in our body and they allow us to react as fast as we could. What do you think would happen if we were able to come up with an even better dielectric for our neurons? Anyway, thanks for watching.